All right, so we're talking about the work energy theorem, all right, which says that work is equal to a change in energy. And since work involves something moving a distance, that means there has to be a change in kinetic energy because something has to be moving. All right, so we can set those two formulas equal to each other. We know that work is equal to force times distance, and we know that kinetic energy is 1/2 times mass times velocity squared. All right, so if we have a problem like this, a 3 kilogram bike with brakes that exert a maximum force of 2 newtons traveling at 2 meters per second will take how far to come to a complete stop? So basically we're trying to find the stopping distance. Okay, and so what we're trying to find out is distance. Well, distance is part of work, so it would be force, which we know is 2 newtons, times the distance, which we don't know, equal to 1/2 times the kinetic energy, which is mass, 3 kilograms, times 2 meters per second squared. All right, and if we set that up like this, all right, we can solve this. All right, 3 times 2 squared, 2 squared is going to be 4. Now, notice that will also square. Oops, there should be a square right there. There should be 2 meters per second squared. And after you get done with that, your answer would be 4 meters squared over seconds squared. Okay? And kilograms times that is going to give you joules. So kilogram times meter squared over second squared is going to give you your units is going to be joules. All right, joules, right? And so 3 times 4 is 12, divided by 2 is 6, divided by the 2 newtons. It's going to end up taking 3 meters for this to stop. Now, something to keep in mind. If you're going faster, and this applies to cars just like it would a bicycle, say we were going 4 meters per second. That would square to 16, which would be 48, divided by 2 is 24, divided by 2 is 12. Okay? Since this number is squared, it's not just like if you're going twice as fast that you will have to take you twice as far to stop. Since this is exponential, it's squared. As this number gets bigger and bigger, this number gets really bigger, exponentially bigger, and so it takes more and more distance to stop. And so you have to keep that in mind. That's why most motorists kind of underestimate how far they should be behind the car in front of them, because they underestimate this exponential increase as you're going faster. If you're going 60 miles an hour versus going 5 miles an hour, the stopping distance is going to have to be a lot farther. Okay, and a lot of times people end up tailgating or rear-ending someone because they underestimate that. So that's just an example how the work energy theorem can be used to find any of these variables. If we know all 3 of them, then we can always find the missing one, like so. All right. Also, we need to talk about, now would be a good time to talk about conservation of energy. Okay, a very important law in physics. Conservation of energy. And basically this says that energy cannot be created or destroyed. Okay, similar law, there's conservation of mass, which says matter cannot be created or destroyed. Actually, there is one exception to that. If you have a nuclear bomb, matter is actually converted into energy. And so there's also a law called conservation of mass and energy, which says the total amount of mass and energy cannot be created or destroyed, but energy can be changed into mass and vice versa. But we're not going to worry about that for right now. Not accepting nuclear energy, we can just say conservation of energy. Energy cannot be created or destroyed. All right. But for example, if we had the pendulum that we were looking at a while ago, we notice that eventually the pendulum will stop, even though it's swinging back and forth and it should be changing from potential to kinetic. It's eventually going to stop, and that's because some of the energy is being lost. We say it's lost, but it is not destroyed. Okay, energy can either be transferred from one object to another. For example, if you were to, if you're swinging a bat and you hit the baseball, some of the energy on the bat is going to be transferred to the ball. Okay, and so in that case, the bat would have less energy than it had before, but even though we say it lost energy, it would not have destroyed the energy. The energy is still there. It's just been transferred to the ball. Now, or we can say it can be transformed, and sometimes we will use the word converted. Okay, but you may hear either one, transformed or converted, to another type of energy. Okay, so transferred, the same type of energy is transferred from one object to another. The kinetic energy of the bat, it's in motion, is going to be transferred to the kinetic energy of the ball. Transferred from one object to another, same kind of energy. Okay, but when the bat hits the ball, some of that energy is going to be changed from kinetic energy into sound energy, because you will hear the sound and then send out vibrations. You hear the impact of the ball hitting the ball. Heat, if you were to measure the surface of the ball, surface of the bat, and the air around it, there would be an increase in heat. Okay, and so that energy has been transformed or converted into another type of energy. And this happens very often. And for a long time, people couldn't measure all the types of energy, so it was very difficult to prove that energy didn't get lost or destroyed. But now that we can measure heat and various things like that, we can prove that it is not lost, it's just transformed from one type to another. All right. For example, if I can find my picture, let me see what I do with it. Back here. Okay. This is a bicycle tire. If a bicycle tire going around, and let's just say that you slam on the brakes, well, you have this kinetic energy. What happens to the kinetic energy? Well, if you look on this infrared picture here showing heat, you can see that the tire generated heat. Also, you can see heat where it was rubbing on the floor. Now, normally you wouldn't see this, you would notice it, and so people didn't realize that perhaps as much as it happened, unless there were just large amounts of heat. But in this case, you can see that in fact, the tire, so that heat was changed to heat in the tire. Some would say heat on the floor. Okay, and so energy can be converted, but it is not either created. You don't make new energy, nor do you destroy it. Okay. All right. So at this point, we want to talk about what are some types of energy. Okay. So we know that they can be changed from one type to another, but what are some types of energy? All right. Well, some of the common ones, we'll be talking about some of these in chapters to come. Nuclear energy. All right. Relatively new compared to some of the others to us to discover that, but electricity, okay, heat, sound, light, electricity, heat, sound, light, okay, and then potential energy, we've already talked about some of those, but you have gravitational, these are just stored energies. You have elastic, and of course you've already remembered, but I'm having trouble off the top of my head, but you've always remembered the last one is chemical, stored chemical bonds between atoms. Okay, and those are all types of potential energy. All right, now nuclear is probably a type of potential energy because the energy is stored in the nucleus. Okay, so it could possibly be considered a type of potential, but it's not the same as chemical. We need to keep that in track, and we don't usually list it under potential. But arguably, you have this energy that holds the protons and the neutrons together, and it's a very, 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 very strong force. That's why it releases a lot of energy when you can finally break it loose. And we can only break it loose in very large atoms, some of the largest naturally occurring atoms, like uranium. Okay, or we can change uranium into plutonium, which is even bigger, and then it's more unstable. It's more likely to break apart. But it's a very, very strong force, and that's why it releases the mushroom cloud of energy when you break it loose. And it could probably be considered a type of potential. All right. Now, the other ones that are listed up here, besides the potential ones, are technically, you could argue, they're all kinetic. Electricity is caused by the motion of electrons moving through wires and so forth. And so it is a type of kinetic energy. Heat, we'll talk about, has to do with how fast the molecules in something are moving. When something heats up, what we're doing is we're speeding up the speed at which the atoms vibrate if it's a solid, or that they actually move around if it's a liquid or a gas. Okay, so it's also a type of kinetic energy. Sound is vibrations, okay, moving through air, so that's type of kinetic And light, you have light waves that are moving, and so that would also be possibly considered kinetic. I mean, generally we say kinetic, we're just talking about motion, and we talk about these other types as types of energy in their own right: electricity, heat, sound, light. But they could arguably be considered part or kinds of kinetic energy because they all involve motion. Okay, and these could all be changed from one type to another. Nuclear power releases heat, which is used to make steam, which turns turbines, which is kinetic, and so in a power plant. And so you have these different changes from one kind to another, and we kind of take some of these changes for granted. A lot of chemical reactions, you're releasing the energy, or it absorbs the energy. Things get hot or cold when they react, depending on if they're absorbing or letting go. We don't think about springs and elastic, but we have elastic in our clothes, and springs from your pins, all kinds of little things that we just don't see them because they're inside the workings. And gravitational is one we see more often because we think of things that fall off of things if they're up in the air. Okay? But they can all be converted. Now, I'll stop there for a second. Energy is converted to one another. Very often, one of the byproducts of that is heat, and that heat is basically, we say, wasted because we don't harness it. In some cases, we harness it, like when we use the heat from heating up water to make steam, and we use that to turn the generator into electricity. But for many, many of these other conversions, almost always a lot of it is given off. For example, if your car burns gasoline, first of all, the gasoline has what kind of energy? And that would be chemical potential, because chemical bonds, high energy bonds in the gasoline can be broken. And when we burn it, heat it, we use heat and a spark from your spark plug to light it, and that causes it to burn. Well, when it does that, it releases obviously hot exhaust gases. About a lot of that energy comes off as basically wasted because a lot of the exhaust, the heat into the exhaust. One half of the energy produced by your gasoline is wasted on the friction of the moving parts of the motor. Even though we put oil in there to make them slide better and have less friction, still you lose about half of all the energy from the gasoline just on those moving parts. And of course, some of the gasoline doesn't burn completely, and so it's not complete, and so that gasoline runs out the back. And so tends not to be very efficient, okay? And we lose energy on each of those. We'll talk more about efficiency when we get to machines, but just keep in mind when energy changes from one to another, sometimes a lot of it is lost, okay? Another example of conversions, though, in hybrid cars. Hybrid cars are unique. They also, of course, run electricity, but they also, when you're braking, it uses the energy from the braking, and rather than just changing it into heat, it changes that energy and stores it into electricity as electric potential energy, basically, okay, and stores it in the battery. So that would be another, in this case, the electricity would be considered potential. If we could save it or store it in a battery, then it's potential energy. And so in that case, they actually take the energy from the braking, which normally would be just wasted as heat and wearing on your brake pads and stuff, and that's it. Instead, they use that energy and help create electricity, which once again helps the car be more efficient and recharge the battery so that you can run on the electricity and have it when you need it. All right. Now, these are types of energy. We want to talk a little bit about energy sources, and what do we mean by energy sources versus energy types. When we talk about energy sources, or we're talking about the environment and what are energy, we have to dig up things for energy. Usually we're talking about things that we can use to make a particular type of energy, and we usually talk about electricity. Okay, and so what are some sources of, when we talk about energy sources, really we're usually talking about what are sources of energy that we can use for electricity. Okay, now they can be used for other things, gasoline, oil, and so forth, which we'll list on here. Can be used for running cars and so forth, and there's gasoline motors and things like this. But for in general, we're talking about these are things we use for energy, but in particular to make electricity, because we depend so heavily. Gas, oil, natural gas. Interesting that all three of those at one time were just considered waste products, but we didn't have anything to use them on. Once people realized they could burn them and use them for things, and they become very handy. Hydroelectric or hydropower is basically using the flow of water through a dam, usually dam up the water and use